Hello, everybody. Today we're going to talk something about assembly. Okay. So, what is assembly? Okay. Assembly means the thing is much closer to the machine language. Almost the next step towards machine language. Once you do run an assembler over an assembly language, then finally you get the binary. Okay. So that is why you have to know how assembly works. Okay, it is exactly converted. I mean, it is bit to bit converted into the final binary. So you can in fact get the assembly out of the binary also. Okay, so it is just the reverse form that is also available. Okay, that is why you should know binary. Okay. So, in order to know why you should know binary assembly and binary kind of thing is because the final code, the executable code that you're producing for BSD or any kind of operating system or anything, it is going to be in assembly language. Say you have written a C program for Hello World. Okay, so somewhat the section looks like this. Okay, this is how it looks like. Okay, so it has got what is called a global underscore start. Okay, then section dot text. Then after that underscore start colon will be there. Then after that move something, move command, move command. Then syscall move xor syscall section dot data message colon db. Okay, data byte and things like that, and it will be finally filling out. So this is how an assembly code looks like when you generate .asm file or .so file or capital S file and things like that. Okay, so when you're running a compiler, it generates an intermediary code called assembly code. Okay, the final thing before it is going to convert it into a machine language, it is going to generate what the assembly language looks like. So you have to learn all these things, assembly code you have to learn because most of the processors they have a set of instruction set. Okay, so this MOV comes from instruction set of the particular processor. Okay, so each has got different kinds of here it is MOV is for 8086 or something like that. So for other things it will be MOV long or something like that. Okay, so here what he does is you have what are the different things: stack index, data index, then you have data index, then what, stack index, data index, and you have so those are the two things that are called. Okay, so it is all relative. Okay, R means register AX. Okay, register AX is equal to 1. So move register AX, AX is equal to 1, and then move register increment DI. Okay, so register DI is so he is using register A, register D, and register S. S is the stack. Okay, so these are the three things he is using here. Okay, uh, and after that he is just the three elements that he is using is A, D, and S. Okay, so he is using the registers of these three things, and then he is using I means increment. Okay, register D increment 1, register S increment message. Okay, so he's going to the next message and things like that. So message, the next location, the message and things like that. And after that finally he is doing a RDX. Okay, so compare is the one which is going to use. So there are different kinds of assembly instructions that are there. So the basic things you have to know is dot. Okay, so whenever you start something you say section. Okay, section dot data, section dot text. Okay, so the lowest thing will be section dot data. Okay, the below thing, the final thing will be section dot data, and above that it's section dot text. Then above that it will be stack. Okay, so dot ess also is there. So some of the things allow for dot ess for extra stack and other things. extra stack manipulation and other things. So you have what is called a dot directive. So you have to say section dot text. Okay, immediately it knows it's a kind of text. Okay, those are all something to do with instruction set. Okay, so when you say section dot text, then it means it's all instruction set that is going to be there. And when you say that it is section dot data, then it is going to be a data section which is below the thing. So, and above that you have section dot text, then above that you have global underscore start, which is actually the stack segment and other things. Okay, so it is going to, so the stack segment is going to the store the pointer for underscore start, where the code begins. Okay, so it is the global. When you say global underscore start, it means that it is stack segment directive, as to say that the pointer is underscore start from where it is going to start the thing. Okay, so first you have to load underscore start into the stack segment or the base pointer. Okay, base pointer of core segment. Okay, so once you load the base pointer of the core segment, text segment, then it is going to text or code segment. It is also called code segment, or it can be called also called dot text. Okay, text segment. Then immediately it takes from there the set of instructions, starts executing. Okay, so here the commands are move. Okay, then some registers for increment, some registers for message. Okay, so finally it is going to, so if you take RSI message, okay, this is save index message. Okay, so stack index message, so it is going to take it from the stack. Okay, so if it is going to RSI, then it is going to be register relative stack index message. Okay, so from the message, okay, RSI, it is going to find the relative stack index for message, and there it is going to find the data byte, which is called the hello world. Okay, so from there it takes the hello world and prints the message. So the whole thing is just printing that message. And finally, to exit out of the loop, you have what is called a syscall. Okay, syscall is the one which is used for coming out of the assembly code. Okay, so that is taken care of. It when you generate syscall, immediately it is a kind of interrupt generated by the process, saying that the process is over. Okay, the process complete means immediately you call syscall and exits outside the code section, and immediately the processor lets the process ID, and then it comes out of the process table and other things. Okay, which the system will take care of. Syscall means it is system is going to take all of the, so so for entry into the system also you have to do what is called a syscall. So syscall will be the first thing that is called. Then after that it loads the the section, the different section into the memory. Okay, okay, so it allocates the memory based on how much of memory is needed by this particular assembly code. Okay, so based on the amount of assembly code, it is going to fetch some kind of relative addressing kind of RAM. Okay, so from the RAM it is going to execute all these things. From the file system, first thing it will be stored in the file system. The binary will be stored in the file system. From the file system it is going to go into it goes into what is called a queue waiting state. Then from queue waiting state switches over to it goes into what is called a process state, and then it finally goes into what is called a executable state. Once it goes into executable state, then after that the code gets execution based on, so the code execution has the executable code has three different sections. Okay, these sections you have to understand. Section is dot text, section is dot data. So first thing is stack, the second one is dot text, the third one is dot data. These things are all relative addressing. Relative addressing in the sense like where it begins, where it ends, it's all relative. Okay, so relative addressing database is about 10. So here hello world is given uh, 10 data bytes or 13 data bytes which is going to be there. Okay, so that is how the whole thing is starting. So this is a simple thing which you can use for a simple C program like a hello world. This is the kind of assembly language which you can code, or you can write it in the native language, the particular kind of architecture that you are using, which will have some other kinds of statements. Okay, little bit and a little bit different. It will look a little bit different based on what kind of processor you are going to run this hello world section. Okay, so the C program, what it does is compiles these things and finally produce the binary code. If you want to see the binary code for the instruction set, then it is going to look like somewhat like global, like CC00 will be the start address, and CC so from the start address it will be the section byte will be saying CC FF or something like that. So CC, if it is CC, is the one which is the start address of the memory RAM. Okay, so CC00 is the start of the memory RAM. So the first thing it is going to, when you say global, immediately it is going to load that particular CC00 as the first start address for that particular RAM. Okay, so once it starts loading the thing, then after that it is going to execute all these things. So it notes, then immediately the first after the it is a stack pointers, kind of next stack pointer when it is going to increase, then it will just immediately go into the code section, start executing the code, and finally come out. It will use the data bit. Usually the uh, dot data section doesn't get affected at all. In the sense it doesn't do any kind of reading or writing to it and things like that. Okay, it's all related to when you're saying it is moved completely and things like that. Okay, so some data sections might be written or read onto. Okay, mostly they are all done in registers, but sometimes it might be more. So it's a move from memory location or something like that. So memory location will be allocated on the DB section. Say if it needs a structure you are defining, then the structure is going to be in the DB section. Okay, from the DB section it's going to have a relative addressing. So it is going to call that particular thing and fill all the things whatever you want to give. So it is going to fill all that stuff, and then finally it is going to give a syscall and then exit out of the program and then come out, and immediately once it gets the exit signal from the processor immediately increments the stack pointer and then switches over to the next program execution. Okay, so sometimes it will be multiprocessing or multitasking where the switch doesn't have relatively. So for the CPU will take care of some of the things. Okay, if it wants to switch over to some of the things depending on memory allocation. So if memory allocation on other things fails, then it might don't want to switch or something like that. So this is the basic thing of how an assembly language works. Okay, assembly language, when you write something in assembly language, it is just the next step towards the actual compiled binary. Okay, it is actually .exe file, actually something pretty close to .exe file. You can just do a conversion straight away from an assembly code or to .exe. Okay, it's stored in .s or .o or .so or big so or something like that. So those are the kinds of, so it sometimes it might be library also. .o files also have these kind of architecture and things like that. Okay, so as for assembly, this is what is needed. Okay, now let's go into something different. Okay, now as for booting of the system is concerned, we wanted to see how the booting of the system happens. Okay, reserve for 32 bits, bow h, so these are add RSP return. Okay, so some of the things are called, so instead of system, last time we saw something like that, and here it is used as ret. Okay, ret. Ret is another instruction to return to the particular kind of things. So we can use return also. Okay, or np. Okay, so some of the things they use np. Okay, rsp, chcl, those kind of things. Again, we want to go into something else also. Here is the one which is going to be the swap. Okay, So uh, you have the section dot text. Okay, I told you. So it is you're going to start the text file, or it means that it is going to go to the execute. It is going to go. It is the what is the section? The section is going to be what dot text. It means that it is executable code. So what happens? Global swap. So if you're going to switch from one process to another process, you have to give what is called global underscore swap. Okay, so swap is the one which you can define the global inside the dot text section also. Okay, so it is going to so global underscore swap immediately dot text section, and it starts working on those things. Okay, pop return. So finally you can use ret is the one which is going to give away the thing and switch over the process. Okay, return means it's going to exit. Okay, once it exits, then immediately it is give holds to the other one. So here the move instruction has ebp, esp4, then edx and eax, ebp minus 4, ecx, eax, those kind of things. So here he is using e register e alone. Okay, so uh, external base pointer, that external stack pointer. Okay, push EBP. Okay, so first thing is going to save the previous kind of context. Okay, so the first command that is executed is it is going to the base pointer of the previous environment is going to be first pushed into the stack. Okay, so once it is pushed into the stack, then it is the stack has got usually stack pointer of any processor has got different types of processes that is running. So the previous environment where it was pushed, so it is going to push that particular thing into the thing, and then start executing the things, because every time you have to push EBP, because it is if you want to switch, the task is multitasking kind of thing, then you have to give the push EPB base pointer. Okay, so the base pointer is always push first, so that you can have the next. Then you have to move E base pointer to ESP also. So you have to push the from the E base pointer, you have to push the whole thing into stack pointer. Then you have to decrement the stack pointer, because the first three instructions is for just pushing the whole thing into some kind of stack, the environment into stack, and then find the stack environment of the previous process that was running into stack, and or part of the code that was running in the stack, and then you start execute, then move edx to ebp plus 8. Okay, then why he is moving on to ebp plus 8? So because he has to data registers where data register is where it's starting. Okay, so base pointer, from the base pointer about 8 things it has to switch. Okay, so 8 byte is a skip. So base pointer, from the base pointer he has to skip 8 segments, and finally eax to edx, then you have to move eax to edx. Okay, so there he is doing what is called data. Okay, so he is doing the data, EBP plus 8 is the data. Okay, then after that he is using the EAX and EDX, and EBP minus 4. Okay, EAX, then EBP plus 12. Okay, so that is another one. Okay, EAX, EBP minus 4. Okay, so 8. So it is all relative addressing he is calculating. So EBP plus 8, EBP plus 12, EBP minus 4, these are all relative addressing. So based on that, he is doing all the calculations. Okay, he is moving all the steps, and finally he is finally once he has pushed the context of a particular thing, this is called context switching. Okay, so this is the basic thing where it is going to do a context switch from one process to another process. Okay, so when you want to just running some code or something like that, then if it is going to switch over from one thing to another one, so this is what happens. So first you have to push something, and then finally you have to pop the things. Okay, base pointer pop, and finally EBP return. Then after that you go into, from the assembly code you can switch over to the C program. kind of code where it is binary is going to be compiled and things like that. Okay, so workspace dot nasm asm main dot asm, so minus o swap dot ob. Okay, so this is the basic thing of how. So this is just for swapping. So I'm just taking different examples of what is happening. Okay, so basically what happens when you write a C program. So this is the basic thing that is running for any kind of swap structure where it is going to, do your work for from the if you're going to call in a C program with a swap section. Okay, so if you're writing any assembly code, it is going to do these kind of things. Okay, these things you have to do just for swapping the thing. You have to use the workspace and other things. Okay, so another one we will see. Okay, here we will see another one. Okay, here text global swap. This is also move. This is for also swapping. Okay, let's go into something else. So I'm showing different examples of how the thing works so that you have an understanding what is happening. Okay, so here push RBP, move EDX, call this thing, move L, move. Okay, so this is for library creation, I think. Okay, we don't want that. Okay, let's go into the thing back again. So here we'll see. Okay, okay. Here is another example. Okay, so this is where you can clearly see what happens because it has got the binary code also and also the assembly language also on, so that you can have a clear look at how it looks like. Okay, so the command is actually so he has to org is the origin. Okay, RCM plus $0, so begin monitor. So he is writing into the monitor. So from the ROM he is taking 0 as the channel, and then org is the one which is going to load the channel for that particular thing. And for monitor, he's accessing the monitor and start LDS hash stack. So first thing is going to give an instruction of load stack. Okay, and he is giving the hash stack, means the stack pointer of the particular thing. Okay, then because it's C000 is the instruction, so it has got ROM plus 000, and he has got C000. So start LDS hashtag. Okay, so that instruction is going to be decoded as BE0070. Okay, so BE is the uh, B is the instruction, I think. Okay, B is the instruction, and C000 is the start. Okay, so start is here. The previous command was the begin monitor. Okay, so it is going to start is the instruction pointer. So it is going to take in that LDS is the one which is going to have 8000 and 70 is the stack, I think. Okay, so 70. Okay, after 70 bytes or something like that. Okay, then reset A equals. Okay, then he is going to reset. Okay, what is the initialize none? Okay, so he is going to reset equal to person 0010. So he is directly giving the register for the reset of the particular channel. Okay, he is trying to write it on a terminal or something like that, so that is why he is giving the thing. So then you have clear register equals. So then first you have to reset the register, then you have to clear the register of that particular thing before you start writing onto the terminal. So then you have so that reset and clear register are just two instructions which don't have any kind of they are just stored in the next section. So it is 00130011. Okay, so directly it is called. Okay, so once you just go do 0013, it means that it is going to reset that particular channel. Okay, 0010, then you are going to write into the channel and clear the register. Okay, then after that it's going to switch back. So C003, so C00 and C0011. 1 and 2 is the next two bytes. Okay, next two bytes, no, it is a word, I think. So next two words, then after that it is going to be C008 8613. So it is LDA. So he's loading the address. Okay, LDA means load data address A register. Okay, into the A register. Okay, that instruction set will be like 8613. Okay, that will be the loading. Okay, so the address for that particular thing is first 13 is the address, so that is why it is loading that. Then reset, then he have to stack A. Okay, ACIA. So then he is stacking the things. Once it reaches reset address is located there, then he is going to stack that particular thing on a LDA clear register. Okay, then he is going to give the clear register thing. Okay, and stack register ACIA. Okay, so these are the four instructions that are 1 2 3 4. Okay, 8613 8680, these are all hex code. So hex code means there are basically about 2 bytes. Okay, so 8 is the first byte, 6 is the second byte, or it might be 8 6 is the first byte and 1 3 is the second byte. Okay, so it is hex code, that is why it has got that that character set. Okay, then after that stack activate, then you have jump. Jump is also another instruction of assembly language. Okay, equals is one of the assembly language. Okay, jump is another statement of assembly. Then you have stack is another, STA is another kind, LDA is another kind of, STA is an LDA. These are all stack or load or something like that. So those are the kinds that are going to be use LDA. Then ASR. Okay, uh, accumulator shift register. So sometimes they can use shifting also on accumulator. Then BCC, LDA, AND A. So AND is a logical kind of things which can low. LDA means load data address. Okay, AND means adding the contents of accumulator. Okay, jump means you are going to, you can jump to that particular location or something like that. So out CH is the jump thing. Okay, then finally it goes down and index BSR. Okay, then finally goes to and RTS. The finally RTS is called, and then you come out of the thing, then jump clear return. Okay, so once you have written into the channel, this is for basically to write into a register and output something as a character into the input character, and then come out of it. Okay, so this is for taking in input basically. This is for the register of the input register. Okay, so there are different kinds of assembly code. So some of the things we saw, we basically why we want to see all this assembly code is you have to, when you're writing a C code or something like that and you want to debug it or something like that, when you're writing an operating system, then you want to go into this. So basic structure is like this. Okay, you have this here, you have this kind of thing structure here. Okay, then after that once it goes into an assembler. Okay, then finally you have the bit form. Okay, the machine code will be somewhat like this. Okay, that is what the thing is. Okay, so this is how it looks like. And if you see any kind of binary .exe file or .bin or .xx file or .cx file or something like that, it is all X means it is going to be executable, things like that. So it will be all, any executable will be all kind of binary file or hex format. So if you want to decode the complete thing, you take any exe file and say hex dump. Okay, so once you do a hex dump, it will be, you have to find out what are the 3 different sections of the hex dump. So first thing, you usually cannot identify where the code section starts, where the data segment starts, and where the stack segment starts once it is converted into a binary. That is why you have to do it. You can do a disassembly of that particular thing and then convert it to an assembly and then exactly find where the different segments start. So you have to have, sometimes it has 3 segments, sometimes it has 4 segments. Okay, so the disassembler helps you to kind of taking from binary and then converting into some kind of assembly code which you can recognize. Okay, because below the assembly code you cannot recognize anything what is happening or something like that, because it's very difficult to go and decode something in hex code or something like that, or final binary kind of thing. So you can use a disassembler or something like that, or a decoder or something like that, then you can use it. Okay, so this is for how to kind of like when you are going to debugging some of the things of assembly code or BSD systems or Unix systems or I think other kind of operating systems. Okay, so this is an introduction to kind of assembly kind of thing, so that you can have what is the kind of stack that is used. So first thing is machine. So what happens is when you're writing an object-oriented program or visual language or something like that, then it gets converted into any one of the lower forms. Okay, so you're dragging something on the screen. Okay, and you're putting and you're writing a code for display of something, then using visual language or something like that, then for the first thing it converts gets converted into Java, C++ or Pascal. So that is the language it first gets converted to. That is called a high level language. Okay, so then it is going to uh, that is called high level language. These are called high level languages. The next level, it goes all this when you write something in Java, when you write something in C++, or you write something in Pascal or visual language, then immediately those are called high level. Any other kind of Python and something like those are all high level language. Those first layering is those kind of things. So V basic also is a kind of high level. Scripting is one step above these things. Okay. So first level will be high level language, then it will be assembly level language, then finally it will go into machine language. Okay, this machine language, once it's all zeros and one, these zeros and ones are going to drive the hardware, which is going to be the processor or IO or registers or locations of different hardware kind of thing, or it can be a serial port or parallel port and those kind of things. So finally the machine language is going to write on to different kinds of based on the processor what it does. Okay, those kind of things are there. Okay, so this might be enough for today, so that you have a brief overview of how the thing works in an assembly code and why you need to know some of the assembly codes and things like that. So each the assembly code instruction set you can just go look up for RISC, or you can look up for Intel, or look up for 386 or 486 586, 686, even 686 you can go look up it, because so in case of parallel processing there might be a little bit of different kinds of instructions that if you have multiprocessing and other things coming in. Okay, so these text segments and other things are going to be a little bit different. So they may not be because mostly assembly languages are all very close to each one of those, kind of any kind of hardware is going to use a basic few set of instructions which are, you can write the same assembly code onto other machines also, because assembly close is really close to the machine. So that is why they don't change much. But some assembly directives might be supported in some of the process, some assembly directives may not be supported in some other processor. That is the only difference, or probably there's some kind of scripting difference. Okay, depends on whether it is a RISC processor or some other kinds of processor architecture. So the basic assembly code will differ only in processor architecture. Okay, architecture in the sense they have different types of like Intel, AMD. AMD and Intel are the same, but RISC is going to be a little bit different, because it's going to high-end process and things like that. So that must be enough for today before you start coding on BSD languages, an assembly language for BSD or Unix system.